Pleasure to be here today to talk a bit about SDVs and how we can solve specific challenge in the automotive industry with our Zetta Auto product. Let's jump right away into the presentation. Just wanted to spend a few seconds to introduce ourselves, since today you're going to have two speakers. I'm Emanuele Visconti. I'm in the product management team at TTTech Auto, and my background is mainly in robotics and automotive industry. I studied technical from the engineering perspective in autonomous systems and controlling engineering, and I'm currently in the team in product management. I handle mainly, and I'm responsible mainly for product over the area of communication and of functional safety. Fanny, you want to say a few words about yourself?
Absolutely. Thanks, Emanuele. Great introduction. My name is Fanny Gangula. I'm Senior Solutions Architect at ZettaScale with over 12 years of industrial experience in communication technologies. So ever since I graduated, I've been working with communication technologies. I worked in several industries, including building automation, aerospace, and automotive. I'm also representing ZettaScale at Eclipse IoT Working Group as a steering committee member, and also very active in Eclipse Software-Defined Vehicle Working Group as a supporting member and taking part in initiatives that are happening around in these working groups in Eclipse Foundation. About ZettaScale as a company as its headquarters in Paris. We have R&D offices in Paris as well as in Netherlands and Hengelo. Although we are based in Europe, we have few colleagues working in Asia as well as in the United States, helping us locally with the requests coming from these regions. So with that, let's dive in, Emanuele.
Sounds good. Let's start then. So before to even get to the actual solution, right? We let's dive into why we even proposing Zetta Auto, right? And what are the challenges that we are trying to solve? Definitely, I will start from the SDV, right? SDV currently is the main word. Multiple stakeholders within the automotive industry are talking about it, and it is a transformation. It's transformation in terms of switching to electronic user experience and bringing in a bunch of features that are now increasing, right? The scope of what a vehicle used to be within the automotive industry. When we talk about connected mobility, we talk about the autonomous driving perspective. And not only, SDV does not stop within the car itself, but actually it brings all the features in terms of upgradability, being able to continuously update the car. So in this case, we are basically seeing how the car industry is changing in the coupling. What is the software level of the architecture of a car with the hardware, right? We have seen already, and we will see even more in the future, models in which there will be, for example, subscriptions for features. There will be only software and will be delivered on top of the existing hardware. And by doing this, there is a transformation also in the vehicle lifespan, right? Vehicles and the hardware will actually increase the time duration within the actual production life, while there will be new features that are delivered within the whole life cycle of the actual vehicle. And definitely this is driven and also possible by the exponential growth of the SoCs in terms of performance, right? Now we are having already SoCs that are much more powerful, and this computational power is definitely increasing exponentially. What does it mean for the architecture perspective of the car? Definitely, we have seen a trend already, right? In the past, from the E2E architecture perspective, we used to have cars that have a lot of small microcontrollers and each of them is handling few of these functions. We are moving already nowadays in a domain kind of architecture where we have few domain ECUs that are more powerful. They have larger scope in terms of functions, and we are moving toward a centralized architecture where we have the few main central computation and and few the other zonal issues that will take care of the specific scope of the zonal vehicle. So this all transformation is leading to obviously being able to handle of this of the architecture is moving and being able to handle the complexity. And by increasing all this amount of feature that SDV require, flexibility, upgradability, just to mention a few of them, we will see that the complexity, and we're already seeing how the complexity within the software of a vehicle is actually exploding. And we need to we need to kind of evaluate what we actually need to achieve, right? Because within the automotive industry, automotive is a safety business. So we actually need to get to a production, to a start of production milestone where the system is actually safe. And functional safety actually means determinism, right? Like means that we basically are able to predict when what happens when the car is starting, what happens during the runtime, being able to say, okay, this is predictable, this is deterministic, this is actually safe. But in order to get to this level, so far we always been using frameworks that are bringing, of course, this safety, but also were very rigid, right? And this really, in a way, clash with the flexibility that we require within the development, because in order to handle all this complexity, we'll be able to do rapid prototyping, to deploy and to configure the system in timely manner. So there is a clear tension between the desired flexibility that we require during the development and the required determinism that we actually need in actual operation during the production. And with SDV coming to the game, definitely this is getting to its limit. And obviously, we don't want to forget, because this is already here, and we need to be ready for it, right? Like SDV doesn't stop in the vehicle, but it's towards the connected cars. So, Fanny, what can you tell us about the V2X challenges?
Well, absolutely. So by 2030, 80% of the cars will be connected. So you can imagine the massive amounts of connectivity aspects that would come into the picture, and the challenges that we are tackling today is in terms of V2X communication. We are expecting, or some of the projects are already doing the platooning, where we have trucks, and the first car, which is basically our first truck has to communicate with the last truck using a mesh topology, where they communicate without having a direct connection, right? And also at the same time, the vehicles have to communicate with the edge infrastructure and leverage on the 5G infrastructure, which would be out there, and also provide the capabilities where you can decentralize the communication without having to leverage on a central system where you push everything to a central cloud. So protocols out there, they impose certain architecture on you. For instance, if you take MQTT, basically provides you a client broker architecture. So all of them is pushed into a single central cloud. Imagine if you have thousands of vehicles out there in a given region, if there's a sudden disconnect and reconnect, there's a huge TLS storm that will be going towards this broker, and which basically gets this broker down. And so it's basically a zero-day attack on your broker, which causes, of course, the cybersecurity issues and so on and so forth. So we need a certain decentralization and localization method so that the vehicles can communicate with the roadside units and this edge infrastructure very seamlessly. So how do we address that? How do we address the rigidity aspects and the connectivity aspects? Let's dive into that, Emmanuel.
Exactly. Then that's exactly the point. How do we solve these challenges? Well, that's where we are into today, right? We are basically joint forces. TTTech Auto and ZettaScale created a partnership in order to deliver a product that is able to fulfill those use cases in the area of SDV, when we talk about flexibility, when we talk about safety, and when we talk about connectivity. So here, in this partnership, we are fusing ZettaScale decade of experience and expertise in creating communication protocols, and on the other side, TTTech Auto expertise in providing safety solution for automotive. So at the end, the fruit of this partnership is Zetta Auto, which is designed to fulfill all of these needs. But let's see what is Zetta Auto is based on. What are the main technologies? We have Cyclone DDS on one side and Zenoh, right? DDS is the main focus, is the main technology around Zetta Auto. And the reason is obviously this distributed architecture, is data-centric approach. The solution is actually based on open source technology, so Eclipse, Cyclone DDS, and Eclipse Zenoh. And we have seen already how there is a huge list of adopters that are using those two technologies. So you could say like of this is like, I would say the open source is becoming really important nowadays also in automotive. That was a business that usually was a bit more closed source. And so let's dive a bit into what does it mean DDS, right? DDS means data distribution service, and is actually a data-centric publish subscribe middleware. So what does it mean? Actually, here we have a bit like a bit of kind of a paradigm switch with respect to what we used to design, how we used to design our systems. In automotive, we went from designing communication from end to end and point-to-point communication with using signals, and then going to the service-oriented architecture, in which we are starting to losing a bit this how tight is the old system. And DDS here is bringing a next level of flexibility, because as the name says, it's a data-centric middleware. What does it mean? That data is in the center of this architecture, and this this designed for distributed system. So publisher and subscriber, writers and readers of all this data only requires the data. Okay, so data is topics in this case. That's how they call in DDS, are the contracts between the communication. Receiver and sender only require those data, and this brings definitely this kind of push in terms of being able to manage all this flexibility and complexity by only relying on the data perspective. But then what does it mean? We usually we always get this question, right? Like the next question in automotive is how this compare to actual SAM IP. This is I would say on one side it might be not a super fair comparison, because SAM IP is mainly focusing only on the communication protocol side, and obviously it can work standalone, but is mainly working within AUTOSAR environment, while DDS is a full-fledged middleware communication. So it's more like it brings on the table much more feature. When we tackle the ecosystem perspective, SAM IP is definitely automotive, right? It's been designed from automotive for automotive, and usually industry stakeholders likes it. But they also are aware that the talent pool gets quickly restricted when we going to implement a technology that is only implemented in one industry. And on this side, DDS is a proven solution in aerospace and defense, and is a standard in robotics. So definitely the talent pool, and to be able to find that expertise will be much more easier. When we jump into the actual feature set, which is, in my opinion, the main reason why DDS is leaning toward, automotive is leaning toward DDS, right? Definitely, the coupled communication is one of the key aspects, right? We are bringing this flexibility to the next level, as I was mentioning before, and now the only thing that matters is the data. The system doesn't need to know where the sender is sitting, or when the receiver is actually needs to receive the actual data. Even during the runtime, publisher can join later during the system. Subscribers can join later and receive data that has been sent a while ago. So there is a bunch of more flexibility that is now brought into the game that allows now to quickly configure and deploy a system. And then we can jump directly to the standardization aspect, right? This is a very important aspect, because of using a standard allows to don't have this vendor lock-in kind of feeling, right? There is more more clarity on what to expect from the APIs, and this is defined within the DDS standard, that is OMG standard. And when we mention quality of service, I would say quality of service is in the second very important aspect that we are bringing in with DDS. What does it mean? Now, data is the most important thing, right? We defined, okay, this is a distributed system, this is a complex system. And we don't only rely on how the data is defined, and but you can actually define and specify as a user what is the quality of the data that you want to receive. Think about being able to actually specify what is the maximum latency for your messages, or what is the depth of the history of your message. So how many samples you actually want to receive from the past. And this is definitely something that DDS already bring out of shelf. It's included in this communication middleware, while some IP specifies within the more within the AUTOSAR part, but he always kind of expect that there is a kind of a higher level API to implement those kind of logic in terms of synchronization or more complex quality of service. And when we jump to the security perspective, it's SDVs is always like when we are mentioning SDV, we're mentioning connectivity as well, right? So security now becomes also a crucial aspect within automotive, and DDS supports DDS security standard, which is defined in the OMG standard as well, while some IP itself does not, specifying a specific security protocol, but it mostly relies on the underneath transport or on the upper level or external kind of security features. When then getting to the last point, third-party support. Obviously, some IP is supporting and designed for adaptive AUTOSAR. It works with we can work with classic AUTOSAR, and it can be hooked in with ROS2. While DDS now is being defined also as the alternative, right? So it's actually a way a solution for AUTOSAR as well, mainly for adaptive AUTOSAR. With classic AUTOSAR, there is no standardization of it, no, but there are let's say vendor-specific implementation out there. And with ROS2, definitely we are fully there, as DDS is the main communication middleware for ROS2.
So, Emmanuel, if we want to quickly summarize what we have explained in two slides. So DDS decoupled mechanism gives you a kind of a hands-on, let's say, freedom to develop applications. And if you have group of people, group of engineers working on different systems, they can now have a system design, which basically where you design how your services are, and you assign quality of services. The quality of services allows you to say which data is important, which data is not important. And once you have this understanding among your engineers, now you can go to your places and start working on the system independently without having any other communication, and at some point you come back and integrate the systems more effectively. So the quality of services and the services which you define happens before, so you spend a lot of time in system design, but it gives you the freedom to work independently when you have different engineering teams working on different parts of the system. On top of that, when it comes to TTTech, they have the tools like scheduling, where you can schedule the tasks, and you can also add the TSN support to that. So by hooking up quality of services with the TSN support as well as with the scheduling tooling, which comes from the TTTech, makes the stack a very deterministic and safety, brings the safety aspects as well. So I want to ask you one thing, Emmanuel. So what is the experience of automotive industry when it comes to developing applications in traditional frameworks? How long would it take for an engineer to change the application, compile it, and run it on the device using the traditional frameworks? What their experience so far?
Yeah, very good question, because obviously this is one of the things that we are trying to solve, right? And I remember honestly when I joined automotive industry as a robotics engineer, I was surprised by the amount of steps that needs to be actually achieved in order to configure and deploy and test that system, right? And here we are thinking about having a more complex system. Actually, in a way, we are going toward like a vehicle that is more like kind of a robot. And with the current existing frameworks, the time to actually get to the right configuration, to create the right instances, to create the right services, to map it to the applications, to then derive a deployable configuration. This can really take weeks, and that's what we are trying to squeeze up at the end.
So basically, the engineers are working to configure the system rather than developing them, right? It's a differentiator part of an OEM or automotive company is their application, right? This application is greater than that application from that OEM. Instead of working on that parts, they were basically doing the configuration and getting the things done. So I think we need a paradigm shift, and that's exactly what we try to enable the engineers out there to be more productive and effective through frameworks like this.
Exactly. I completely agree with you. But let's jump also on the introduction of Zenoh and why we actually introduced Zenoh within the Zetta Auto. What can you tell us, Fanny?
So Zenoh is a protocol that can scale from the smallest microcontroller up to the cloud. And we do that by providing just three simple abstractions: pub, sub, and query. The pub sub deals with high-speed communication, the communication between sensors and actuators, real-time data, high critical data. And query tackles data at rest, so the data stored in a storage or a computation, a live sensor data which has been queried upon where the sensor data is sent to you. And we does that in a location transparent way. So it is a more generalization of RPC, but provides you this location transparency. That means you don't have to know where your queryable is. All you have to do is to query for the data, and Zenoh takes the shortest path to the queryable and gets this information. It could be a storage or it could be a computation that replies to your query. On top of that, Zenoh comes with high performance. There have been several white papers out there that proves the performance of Zenoh in terms of latency and throughput. It comes with inbuilt zero copy memory, and we provide an extremely clean and user-friendly API, and we take extra effort for you to write applications without any overhead. And this is something we have got several inputs from our users who are out there. At the same time, we tend to not let you spend a lot of time into the configuration of quality of services and so on. So we kind of provide all of it out of the box so that you don't have to, you can change certain things, but most of the things are inbuilt when you take Zenoh and play around with it. So there are several adapters from automotive to robotics, from industrial automation to aerospace and so on and so forth. So it's a very mature protocol. It's been out there for almost 7 years already. So moving on. So why did we get Zenoh into the mix? Several reasons. So DDS is a protocol that works really well when you have a lot of resources at hand, CPU resources, memory resources, and also bandwidth resources. And this is something very sparse in heterogeneous systems like a car. You have several microprocessors, tiny ones, microcontrollers. You have to be spontaneous. You have to communicate with the world around you. You have to create a sort of situational awareness. So TDS, when you want to scale down or scale up, it runs into several issues. And this is something has been reported by the ROS2 community. They've been using DDS for almost 8 years already, and the users were confronted with several issues whenever they want to put the DDS into microcontrollers or scale it on the unreliable networks or into the wide area network. So this is a report, and these are some of the issues. One of them being DDS has this discovery mechanisms. In a car where you have a static topology, it could not be a problem. But whenever you want to scale this in the wide area network, you basically have to do some kind of workaround to get it scaled into the wide area network. At the same time, it uses UDP as a backbone, let's say UDP multicast, to discover all the things in the system. So as application, you will be overwhelmed with the amount of information that will be sent to you as a DDS application. You discover all the readers, you discover all the writers, participants, and so on and so forth, although you are not interested in it. So that makes a huge difference when you want to scale up, right? And And they were running into situations where there are robots in a factory unable to communicate. They were finding themselves in endless discovery mode, right? So this is something, yeah, that was the situation with the discovery overhead that has with DDS. So, and if you remove all the features of DDS, and if you want to make it as smaller as possible, you get to 2 megabytes of footprint, and this is something you cannot have it on you cannot have it on the smaller controllers. So this is a thing, and at the same time, the other aspect is memory. So the memory requirements the DDS requires is about 2 megabytes. That is something not available for microcontrollers, where you have around 512 kilobytes of memory, and you cannot fit it so well into the microcontrollers. And on top of that, the message of DDS requires 52 bytes of overhead, and also requires a lot of processing on the microcontrollers and takes a lot of bandwidth into the account. When you compare that with Zenoh, we require only 5 bytes of overhead. It's almost like DDS requires a tenfold of what Zenoh requires. In certain setups, Zenoh can have almost 3 bytes of overhead. And these are the advantages what we saw, and also the ROS2 community have seen it. And they were looking into alternative middleware for ROS2, and they were evaluating all the middlewares out there, GDS, Zenoh, and ZeroMQ, MQTT, eCall, and so on and so forth. They come to the conclusion that Zenoh fits their requirements very well in the scenarios when they want to scale up or scale down. So that's the reason why we have to also have to provide this option to the users, so that they don't suffer or they don't go through the same problem what the ROS2 community has gone through.
Yeah, makes a lot of sense, right? Like in DDS, as we said, is the core of the solution and is rich in features, but you might not require all those features everywhere, and that costs, right, in terms of performance, in terms of resource utilization. So that's why Zenoh then is there to scale down to microcontrollers and up to the cloud. So here we have a quick outlook of what the solution is about. Quickly, just to mention a few of the main things that we will also go through later. There is the data-centric communication. There is the safety aspect, like being able to have a solution that is safe up to AZD, V2X readiness thanks to the Zenoh router, the optimized stack in the microcontroller, where we want to minimize and optimize the resource usage, and being able also to have the TSN support. Let's jump right into it. So from the solution perspective, how does it look like? We have, you can see here, it's more or less Zetta Auto everywhere, but what does it mean? We have on the left side what we call MPU, which is basically the application cores, the ICUs that are the powerful SoCs that then are able to, where you actually want to leverage all this flexibility and these features and quality of service that DDS has. While on the safety island and on the microcontroller side, we are deploying Zenoh. And here you actually see a bit more what does it mean, where on the powerful SoCs, Cyclone DDS basically as a core technology, and then we build on top our own Zetta DDS, which is the automotive profile, where actually the possibility are multiples, like direct DDS APIs can be used, Aracom can be hooked in, and obviously ROS2. While on the microcontroller side, Zenoh Pico has been integrated with classic AUTOSAR in our standard offering. On the microcontroller, we are mainly offering currently the classic AUTOSAR integration with Zenoh, and then applications are still using the RTE APIs, but Zenoh is running as a runtime, handling the inter-partition communication and minimizing the memory that is required. And you could see also how Zenoh is here deployed as enabler for the V2X use cases. So just to quickly mention, we mentioned about TSN, but what does it mean and why are we bringing it to the game, right? Here, TSN is time-sensitive network. In TTTech Auto, we have a long history of creating deterministic systems. And when you come to the deterministic system, we also mean deterministic communication. The standard that is mainly adopted within automotive is a time-sensitive networking, TSN. And here we built also Zetta Auto around TSN in order to ensure deterministic communication between different partitions. So here there is a quick test of what does it mean having TSN with DDS or not. Here we actually did it based on the open source Cyclone DDS. So this is a test that can be easily reproduced. Beside the fact that TSN tooling is that is the closed source ones in order to be able to actually deploy the configuration for the router. But on the A example here, on the A test, what we have is on the left side, we have actually the producers, that is the yellow one, and the blue lines are in the A1. The graph is the actual subscribers, right? The receivers of this data. What does it mean? What happens then? Because there is a deviation at some point, because within this area we are basically creating we are adding an external agent that is causing a disturbance effect, which actually just means that there is another application that is sending a lot of best effort traffic, and we want to see our main traffic, the one that we consider important, what is happening, right? And we see this deviation because the counter on the subscriber side is starting to deviate, and we are losing packets. Okay, so we actually see in A2 how the counter difference, and it really shows the lost packets between the sender of the counter of the sender and the counter of the receiver. On the right hand side, you could see that when we have DDS integrated with TSN, you actually here don't see even the blue part of the subscriber, because this completely overlap with the yellow producer, right? And even in this test, we are running the external agent, but to enfloat the router with a lot of best effort traffic. But here we are able actually to not lose any important data. Indeed, there is like we are able completely to avoid the loss of data. Okay, so let's jump a bit like in the details of how this solution is built. We have the application cores on the powerful SoCs. We said is mainly DDS, right? Here we are bringing the features and the flexibility of DDS. What is important is the data, the ISDLs that defines the actual data structure of the data that is shared. And this is a sneak peek of the integration workflow. This is standard DDS. While on the microcontroller side of things, we are deploying in Zenoh for the reason that Fanny was mentioning already. We really want to be here as optimized and as efficient as possible, and we are our default offering includes the AUTOSAR integration on the classic side. What does it mean? Software component will use RTE ports to actually communicate between each other, but there is a Zenoh Pico runtime that is integrated as a complex device driver in order to handle the interpartition communication. So, and I think we really need to dedicate a bit more time to understand why Zenoh is there from the microcontroller perspective. And the reason is really coming from the user needs, right? In automotive, we have seen a lot of stakeholders on the industry coming to us on TTTech Auto asking for optimizing the microcontroller stack, because that is definitely the specific area of your architecture that is resource constrained, where you actually have limited constraints, and mainly we are talking here actually about memory footprint. So what is out there in terms of data-centric solutions for microcontrollers? There are three main alternatives. One alternative is to deploy DDS, but this is like, here you will have all the flexibility, all the features of DDS. You could think about having a subset of it, but still this requires a lot of actual resources and a lot of memory. When we get then in a way, the community identified this and try to come up with a solution, right? And there is a standard defined, which is DDS XRC, which is supposed to obviously to fulfill this need. The only issue of this the DDS XRC is the fact that the actual communication with DDS is not standardized. As you can see, you actually require an agent, and this is not standard, but is actually vendor specific. So that's why then we went to the on the Zenoh side. because Zenoh is able to be even less hardware resource demanding with respect to what DDS XRC is able to do. And most importantly here, we are really hooking up with the transparent and lightweight interface with DDS. DDS has an inbuilt interface that is able to hook up with different protocols, and that's what we are leveraging in order to be as lean, as transparent, and actually in a way improve this optimization in terms of memory usage.
Emmanuel, if I want to add a quick point, the agent kind of communication is in automotive safety critical systems is something a no-go, right? And when it comes to Zenoh, we have a tight integration as a plug-in mechanism. It natively communicates with our Cyclone DDS and provides a seamless communication without any single point of failure like an agent design, which is provided in the other vendors, for instance.
Yeah, definitely. Thanks for adding this. Definitely. XRC in this case is bringing this agent, which from functional safety perspective, my functional safety experts in the company will not be so happy because of introducing actually a single pulse of failure. And as we said here, we are trying to both fulfill those flexibility and features that are required for SDV, but at the same time, we need to get to the determinism. We need to get to the safety that is required for production. So thanks for bringing that up.
Absolutely.
Okay, so actually here just few data and few diagrams to actually show why and support also what I was saying, right? Why Zenoh Pico at the end should be preferable to the XRC for the microcontroller perspective. By the way, Zenoh Pico is the C implementation of the Zenoh, which is mainly built in Rust. Yes.
Correct.
So we said we want to minimize the memory footprint. We can see in this diagram on the right-hand side that in all the sessions of the communication, Zenoh is performing better in terms of requesting less memory to the system, right? And you can think also that we are optimizing the memory in the microcontroller, but we are also leveraging Zenoh as a wire protocol between the microcontroller and the application processor. So, and what does it mean that in the wire there is a overhead communication, and Zenoh is able to scale down to 5 bytes as a overhead in the wire communication versus what DDS is able to do, which is around 50 bytes. And not to forget the throughput perspective. From the throughput, we can see in the test that especially when we go up with the higher payloads, we see that the throughput is really scaling impressively. Honestly, when the first time I've seen this test, I was quite impressed to see the difference in performance with respect to what XRC or MQTT are able to do. Okay, let's proceed then. Let's take few moments still to actually get into a little bit more what is Zenoh, what is capable to do. Fanny, what can you tell us?
So Zenoh, as I mentioned, it's a POP subquery protocol, and its core is written in Rust. Rust is, of course, provides us guarantees of memory safety and concurrency safety. Most of the memory leaks issues are closed by using Rust as a programming language. That's an added advantage. So you don't have to be expert in Rust. We have APIs in all different languages, C++, Python, Kotlin. You can imagine writing Android applications for that. We have inbuilt shared memory and zero copy support. As you can see, Zenoh can scale from data link layer up to the transport layer. So you can use famous TCP, UDP. You can also use Quick, as a matter of fact, where you want to seamlessly move from one access point to another access point. On top of that, you can run it on transport layers like serial, Bluetooth, Unix sockets, and so on and so forth. You can even write your own link to PCI Express or PCI interfaces as well. As you mentioned, Zenoh Pico is an implementation of the Rust version in C. So we have a subset of a full-featured Zenoh, which is written in Rust. A subset of it is in C, which is Zenoh Pico for microcontrollers and resource-constrained devices. And as Emmanuel mentioned we have an overhead of as low as 5 bytes. I also mentioned that we can even go below that in some cases where you have stringent requirements. So makes it very suitable for constrained devices and constrained networks, for unreliable networks, and so on and so forth. Moving on.
Yeah.
So the beauty of Zenoh is it's a different beast in itself. It does peer-to-peer communication in click and as well as mesh. So click is what, for instance, DDS does, and mesh is something we also provide. We can imagine platooning or swarm communication and so on and so forth. And we also do brokered communication. So if you want a boundary security, or you can have some kind of, if there's a resource constrained device, it can connect to a broker like a Zenoh router and communicate with the rest of the system. Or you want to just close everything in your vehicle and only expose certain thing to the V2X communication, then you can have your router on your telematics control unit and have it exposed for the V2X communication. And the beauty of it is a client can connect to a router. A Zenoh router is a soft router. Don't think it has hardware. So a soft router at your edge, at your vehicle, or at your edge infrastructure, roadside unit, and so on and so forth. You can imagine something like that. And the client can connect to a router or to a peer to communicate with the rest of the system. And you can have these routers across the wide area network and have it communicate with the rest of the system, where you can have a huge infrastructure where you have placed Zenoh routers in some edge infrastructures and have your Zenoh applications and DDS application communicate with each other. Next one. So these routers, the soft routers at the edge, not only route the data, they have additional capability. You can have plugins to storage. You can have plugins to the other protocols like MQTT, REST, and ROS2 or DDS, and so on and so forth. The storages that you plug onto the routers has these capabilities to store the data, where you can query the data for, and you can have multiple storages and multiple routers across your infrastructure, and they synchronize in the background and they align the data among themselves. So whenever there is a network partition disconnection, when they connect back, they kind of align themselves and have the information same on both sides. And whenever there is a network partition, you still have some redundancy on both sides, so your system continues to work in this it provides a great decentralized mechanism to have you leverage on the edge infrastructure. And of course, thanks to the protocol plugins, you can plug into other protocols. And the Zenoh flow is, you can imagine your custom application at the edge, where it can, for instance, take 2 inputs and send it as a different output. So it's a full package router that is suitable for certain use cases in the edge, and so on and so forth. So moving on. This is a nice demo of what we did. Actually, we did a webinar. After the webinar, we jumped right after that onto the car and put the camera on the car and started streaming the data from the car using the basic mobile network, consumer network, and sending data to the Zenoh router, which is sitting in the Frankfurt, which is then sending the data to our to Zenoh router, which is sitting in our Paris office, which has an AI engine doing the classification of these images and sending back to this laptop. To my colleague Gabriella, who is displaying it. So all of this is done using simple mobile network. So basically, if you use an MQTT protocol for this kind of use cases, it doesn't work. If for MQTT at around 84 kilobytes, the throughput goes really, really down. We have some performance measurements on our blog, on our Zenoh blog. Please feel free to take a look at it. Moving on.
Yeah, I wanted just to mention that this is really impressive. When I saw this demo, how actually we see a car streaming up videos and having a classification completed remotely and streaming back this data, and this actually gives this real-time feeling. And there is a number of like thousands of use cases for this in automotive. Absolutely. From the actual hosting all this power in the cloud, or even thinking about debugging, making sure that you actually know what happens when the car identified something, for SOTIF, even not only functional safety, but also the being able to to actually get to that level of understanding of the dynamics of the system. Imagine
you have the roadside units picking the data and sending this data to the cars, and cars doing some kind of situational awareness and so on. So you can build some beautiful decentralized applications by leveraging on Zenoh for the V2X connectivity. So when you put all of it together, this is how it looks. You have the Cyclone on the microprocessors, on the high computes, and they have Zenoh as a C implementation in the microcontrollers. On your telematics units, you have Zenoh router, or even Zenoh itself to communicate with the rest of the system to the outer world through the help of Zenoh routers. Yeah? And you can have storage as storing the data for you, and you can do thanks to the Zenoh mesh topology, you can do platooning or swarm communication. So it's a full package for you to build a continuous V2X and SDV frameworks using the two technologies what we provide. So to summarize, Zetta Auto, you can see it as a framework where DDS uses as the backbone and leverages on the technologies like Zenoh and leverages on the tools and technologies from TTTech like scheduling aspects and TSN support. So to build your deterministic, scalable V2X and in-vehicle systems and frameworks around that.
Exactly. This is like really kind of a picture to show how at the end we are leveraging both Cyclone, in this case Cyclone DDS, so the actual DDS, all Paradigm and Zenoh, in order to be able to fulfill all the use cases, right? From the powerful SoCs down to the microcontrollers up to the V2X, this is fully covered. What it could be kind of a summary of the offering. Main important aspect here that I really would like to stress is how this solution is built on top of open source technology. We have seen this as a trend in automotive, and this open source technology we mentioned is widely used already by different adopters. Now there is I would say that this offering in this sense is quite unique because users can actually start the prototyping from the open source part of the actual stack and get to an automotive profile solution up to a safety certified solution, all with the same APIs. So like we are really minimizing here the amount of effort and the amount of tedious things that we need to do, and we want to focus on the features. So like we want application developer to focus on the actual logics, and what's happening is then by having a complex solution, because complexity doesn't disappear, right? Complexity moves. We add complexity by adding feature in this system, but we need to handle it in the correct way. What's happening with Zetta Auto, with DDS, with Zenoh, we are embedding part of this complexity and we are exposing configurability. So this is this part of the communication aspect is completely taken care for users. And then we are exposing the possibility to get to the right dynamics by exposing the configuration. As you can see here, there are two main versions of this product. One is the QM, the quality managed product, which is supposed to be used for non-functional safety relevant use cases. Of course, we have the APIs and the quality of service as per OMG standard. We are supporting the security, the optimized stack that we mentioned with Zenoh, and the monitor and the performance measurement tooling, and not to forget the TSN integration. What are we adding on top with the Zetta Auto certified? Definitely, really safety is the priority when we talk about this specific version. So ASIL-D communication stack, we are adding end-to-end protection, static topology, static memory allocation, being able to actually get to that determinism that we were mentioning at the beginning, right? So, and here from open source to safety certified, we actually can see what does it mean getting that flexibility that is required during the development and being able to have a transition, a smooth transition with the same API to actually accept the certified solution. I will close it here. Thanks a lot for having us.
Thanks, everyone. Ciao.